Good morning, class. Welcome to this lesson on Modern 8 hydrogen spectra and the energy level diagrams. Today we will be able to explain the line spectrum of hydrogen and relate it to an energy level diagram. So, all elements have what's called an emission spectrum, or a line spectrum. And this is pretty simple. If we take an element like hydrogen and we put it in a tube, looks like this. So there's hydrogen inside here, and then we put a lot of energy inside, and so we hook it up to a voltage. This will start glowing, and what will happen is if we look at this through a spectroscope, what we'll see is a line spectrum. We'll see this. So it'll be all dark except for a very few spots that have lines coming up, okay? And these lines are at very, very specific values, okay? These lines are at very, very specific values. So where do these lines come from? Well, they come from the absorption. So if we have hydrogen and we have an electron, these electrons are absorbing energy from the voltage source, and then they are going back down and they are emitting a photon. Because these are discrete levels, okay, this photon has a very, very specific wavelength. And so these lines correspond to those wavelengths. So if we know these lines, we can figure out the energies. We can figure out the energies associated with different energy levels. So that is a line spectrum. All atoms have a line spectrum. All elements have their own spectrum. These spectrums are even called the fingerprint of the atom because these spectrums will tell us exactly what an element is. So let's go back to Niels Bohr and his energy level diagrams. So we have different energy levels. These energy levels are denoted by the letter N. Okay, these are the different energy levels. And this is an energy level diagram for hydrogen. And you can see here, so n equals 1 is called the ground state, and everything else after that, n equals 2 on, are called excited states. And you'll notice here there's a really big gap between the ground state and the excited state. So we can tell here that it takes the most energy to get it out of n equals 1 to n equals 2. So n equals 2, n equals 3, n equals 4, n equals 5, until finally we get to 0. And at 0 up here means the electron has been removed from the atom. Okay, so it had energy, and if we put in 13.6 electron volts into an electron, it will now have 0 energy, and it'll be out of the hydrogen atom. So this energy diagram corresponds to an electron. If it gains energy, it can be excited to n equals 2. If it gains energy, it can be excited to n equals 3, or n equals 4, or n equals 5, etc. Okay, so that if it gains energy, it'll go up. If it loses energy, it'll give off a photon and it'll go down. And so it can correspond between any of these levels here. Okay, 13.6 being the magic number for hydrogen. So this relates. This is the full hydrogen spectrum, emission spectrum. This is the full emission spectrum for hydrogen. Okay, and what we find is that these energy transitions here, these energy transitions correspond to these lines on the emission spectrum. So if we calculate the change in energy from here to here and get the wavelength, that'll give us this line spectrum right here. So all of these different transitions correspond to the line spectrum here. And what we found later on, for like the Balmer series, this is called the Balmer series because the Balmer series is the emissions that happen for visible light. You can see here they all end at n equals to 2. And for example, the Lyman series here, these are all going to n equals to 1, and this is all UV light, which we don't see. So this spectrum here corresponds to these energy level transitions here. Okay, so energy levels, switching between these two go hand in hand. Okay, and from these energy levels, we can calculate the wavelength of the photon emitted, which is what we're going to do in class. Now, there's one more equation I want to give you, and it is very simple. If we want to know the energy for different levels, we're going to use this equation right here. This is what something else Bohr came up with. Energy of n is equal to negative 13.6 electron volts over n squared, n being the different energy levels on this diagram. And so what we're going to do is if we know the different energy levels, we can calculate the energy transition between those two, and that's what we're going to be doing in class.